Hello everybody, I'm Donghyeon from Kwon University of Science and Technology. I'm glad to present our work, Self-Supervised Learning of Semantic Correspondence using web videos. This is joint work with my academic supervisor Suha Kwak and Minsu. First, let me briefly explain about the task of semantic correspondence. The semantic correspondence aims to establish reliable visual correspondence between different instances of the same object category. As you can see in the figure, each paired image has correspondence between different instances of the same object category. However, there is a critical obstacle to learning more robust matching, the lack of large-scale densely annotated data for training. Because manual annotation of point-to-point correspondence is costly, since the number of image pair and that of keypoints to match are both huge. This table shows that various datasets for semantic correspondence with their features. Overall, they have limited amount of data with small keypoints. To address this issue, self-supervised learning strategies have been incorporated into a semantic correspondence model. One example is to synthesize image pairs with ground truth correspondence by warping a real image for training. However, such synthetic geometric transformation usually fail to simulate intra-class variation exhibited in the real world. Another approach to dealing with the issue of limited training data is weakly supervised learning, which utilizes only image class labels that indicate if a pair of images are of the same class. In this paper, we tackle the issue of limited training data by learning with web-crawled videos. The reason for leveraging web-crawled videos are twofold. First, videos are abundant and readily available on web repository like YouTube, and thus allow us to construct a large-scale training dataset. And second, two temporally distant frames sampled from the same clip often well simulate common inputs of the semantic correspondence task. However, using web videos for running semantic correspondence introduces new challenges such as failures of video retrieval and unreliable pseudo-correspondence labels. By so, we need specialized methods for both dataset construction and learning using web videos. Therefore, our algorithm examined the retrieved videos by classifying their thumbnail images so that only videos with correct thumbnails are downloaded. Then each downloaded video is divided into clips with no abrupt transition that guarantees stable space-time correspondence. Our next step is to generate pseudo-correspondence labels for the video clips. To this end, we first establish dense space-time correspondences for every pair of consecutive frames in every clip by training and deploying a self-supervised space-time correspondence model with no human intervention. The established space-time correspondences are then used to derive pseudo-correspondence labels between any arbitrary pairs of the frame images. Since consecutive frames of each clip show smooth motion, the model can be trained stably and accordingly build a correct correspondence between consecutive frames. The learning framework mainly utilizes the web video dataset constructed in the previous section, along with the common dataset for the task. For supervised learning using web videos, we train our model with average endpoint error with pseudo-ground truth correspondence. Also, we adopt a domain adaptive learning technique to mitigate possible negative effect of the domain gap between the images of the common correspondence dataset and web videos in the feature space. Then the training objective is jointly optimizing both supervised and domain adaptive losses. Our self-supervised method achieves the state-of-the-art on 3 benchmarks dataset in every setting. Also, we conducted a comparison between our method and recent state-of-the-art strongly supervised models. We employed transfer learning, where the model was initially trained on pseudo labels from web videos, and then fine-tuned on the target common dataset. Our model also achieves the state-of-the-art performance on 3 benchmarks. Here are the qualitative results of our method on SPR71K dataset. And here is qualitative results of pseudo-correspondence labels on web-crawled videos. We randomly sampled 8 key points for pseudo-correspondence labels of each frame pair. Note that source and target frames are augmented differently. Thank you for listening to our presentation.